Hey everybody, welcome to section 10.2. It's called regression, or perhaps you've heard of lines of regression. So if we're proceeding through chapter 10 and we have found that the value of our correlation coefficient is significant, so remember we did a hypothesis test using our R method, compare it with our critical value from table I. We rejected H sub O, that rho is equal to 0, so we think that there is a significant relationship between the variables. Then we can determine the equation of the line of regression. So now that we actually know that there is a line, sometimes it's a weaker relationship, but it's still there. So if we found that it was significant by rejecting H sub O, we can move forward from section 10.1 into section 10.2. So the purpose of the regression line, it's called the line of best fit. So what does that line look like? We know it's linear, so we're actually going to be modeling this on the y equals mx plus b equation. We can use this to see a trend, right? We know our rate of change and all those things. And we can also make predictions on the basis of our data. So what if our independent variable is 5,000? What would that mean for our dependent variable? So let's just launch right into these equations. So now that we've done our hypothesis test, please notice our formula for our regression line, or our form, is y prime, or y is equal to a plus bx. It looks a lot like mx plus b. Do not overthink this, because the b in this case is your coefficient of your x term. I know that it's backwards and it's not what we're used to, so just think right here. So in order to find our a value, here's the great thing. The formula is a little bit messy, but we have all this information from when we calculated r, and then we use that r value to do our hypothesis test. So a is equal to our sum of our y's times the sum of our x squares minus the sum of x times the sum of xy, and in the denominator we're going to do n times the sum of x squared minus the sum of our x's squared. This is our y-intercept. Our b value, which is the coefficient of the x term, which we all know, right, is our rate of change or our slope. Our b value is the n times the sum of our x times y's minus the sum of our x's times the sum of our y's, all over the identical denominator for our a value, or our y-intercept, n times the sum of x squared minus the sum of x squared. Please round your values of a and b to 3 decimal places, just like we rounded our r value to 3 decimal places. So, I know it looks complex, but we've got all these things, all of our sums, and we've already probably potentially calculated r. So all it is at this point is just more plug and chug and making sure you've got your calculator figured out. So here's our procedure. First thing we're going to do, we're either going to make a table to find all of our sums, all of our x times y's, all of our x squares, or we're going to enter x, y, and x times y in the TID4. And in step 2, we're going to jot down the sums of all of our important things: x, y, x times y, y, and y squared. Did I say that right? You got all those. And then step 3, we're going to insert those into the linear regression A and B formulas. So we're going to find, again, when r is significant, we are going to find A, we're going to find B, and we are going to put those into the equation, and it's going to look something like mx plus b form. Again, if we've already found that r is not significant, we would not be doing all of this stuff, and hopefully, if they're related, we've already found all of those sums. So let's go back in time to section 10.1a. We did an example, and I'm pretty sure we made a scatter plot about the number of absences and is there a potential relationship with the final semester grade. And I'm pretty sure that our scatter plot showed a negative relationship. That was in example 10.1. 10-1. Scatter plot. Negative relationship. So in other words, more absences, grade lower. So as one increases, the other decreases. Then I'm pretty sure that we skipped, no, we did section or example 10.3, and we found R, and R was equal to negative 0.944. So we've already actually done all these things. Back in section 10.3, I'm just going to fill in my sums as well because we did do these. Sum of x was 57, 511, 37, 45. X squares were 579, and the sum of our y squares were 38,995. So if you go back to 10.3, example 10.3, in section 10.1b, we did do this. Or maybe that was in 10.1a, I'm not sure. But then we didn't actually do the hypothesis test. So before I get to finding a regression equation, I have to actually show that there is a significant relationship. So way back in example 10, whatever it was, when we were going to do the hypothesis test, we know that n is equal to 7, and I said I'm going to do a hypothesis test right down the side here with alpha at equal to 0.05. So h sub o and h sub 1 are going to be equal to rho equals 0, so no significant relationship, or rho is not equal to 0. There is a significant relationship. My critical value, so it's positive and negative. Remember, don't forget your degree of freedom equals 5 because it's n minus 2. And with an alpha at 0.05, I've got a 0.754. I think that's right. Positive and negative 0.754. Step 3 is already done for us. We found back in example 10.3 that R was equal to negative 0.944, which means, remember, I'm going to erase this in a second, but if we know that this is positive 1, negative 1, here's 0.754, negative 0.754. So will negative 9.944 fall in the shaded rejection region or the non-shaded? It's going to fall way down here, super close to 1. So that is definitely a reject H sub O, which means we don't like this, we like this, right? If rho is not equal to 0, we definitely think there is a significant relationship between the number of absences and the final semester grade. So now that we've found that there is a significant relationship, now I can go forward and I can, because what's the point of finding an equation of regression if there's not a significant relationship? That's a waste of your time. So I'm going to go ahead and I'm going to find my a and b for my y equals a plus bx. So I've got all my sums here, so I'm going to start plugging these things in. So a is equal to a 511, and you can do this, right? I'm going to go ahead and hit pause. I'm going to finish filling out, substituting values into my a and b equation, and then we can make sure that you've got the calculations. All right, and are your formulas looking something like that? So there's all my values, my sums filled in for my a and my b. So when I calculated this, again, make sure that you verify and double check you got the calculator down. I ended up with a is equal to a 100 2.493. I know it seems a bit excessive, but I think we just said that we need to make sure we go to 3 decimal places. B is a much smaller value. Remember, B is the slope. I got a negative 3.622. Now remember how we said our R value of negative 0.944 and our scatter plot both suggest a negative relationship, right? So my slope is actually negative 3.622. So if I go ahead and put these values into my y equals a plus bx, which I know some people don't like because it's not what we're accustomed to with our being trained in mx plus b form, I've got myself a 102.493 minus 3.622x, or if you prefer to do plus a negative 3.622, whatever makes you happy there, but 3.622 does need to be negative. So I've got my equation of regression, and then I might ask a question. We can just talk about it. Actually, I'll come back to it. We'll ask a question in just a minute. So I'm going to flip to the next slide. Again, verify that you got the same math. Extrapolation is just a prediction. It's making a prediction beyond the bounds of the data. So maybe it's values in between, maybe it's extremely large numbers, things like that. So it's beyond the bounds of the data. So it's using that trend, using that rate of change to figure out, well, what would happen if this were our x value? Or what would our x value be if we got this dependent variable? So making predictions beyond the bounds of the data. So if I go back to this same example, I might ask something like, with my equation here, what would happen if a student missed, I don't know, 10 days? What would be the trend? So if x equals 10 days absent, what could we predict or extrapolate their semester grade would be? So we'd plug that 10 in for the x. We just do ourselves, oh, I should have put y prime equals 102.493. I forgot to put that in there. Whoopsie. There we go. So I need to just put that value in there and do some math. So if I put a 10 in, y prime is going to be equal to, so my prediction, if a student misses 10 days, I could predict that a student is going to get about a 66.273. I'll call it percent. Right, so it's basically an ordered pair for that particular situation. So extrapolation, again, is making a prediction beyond the bounds of the data. So here, forest fires and acres burned, I feel like we've seen this example before. Is the number of fires related? So in other words, we're going to figure this out. So it says to draw a scatter plot. It says to find the correlation coefficient, R. Determine its significance. So that's a hypothesis test. If significant, find y prime. So in other words, y equals a plus bx, y prime equals a plus bx, or our linear regression equation. And then it wants us to predict the number of acres burned when x equals 60 fires. So we would take this 60, place it into the equation, and do the math. So once we get through section 10.2, we're using every skill along the way that we've done. That is it for section 10.2. That's it, but a lot. Hopefully you've gotten all the bits and pieces along the way and got your calculator down. Have a great day, and I'll see you next time.